Hi, and welcome back. We're halfway through this chemistry stuff, and now we're going to start learning about macromolecules. And so, first, I'm going to do a short overview of what organic molecules are, and then we'll move into carbohydrates. So, what does the word organic mean? I want to stop for a second and give you a chance to think. So, yeah, you're going to listen to silence for a few seconds while you can think and come up and say out loud, what do you think organic means? Okay, well, I know from having asked this question in class many times that students come up with answers like, oh, it's natural, or like, it's a very organic process. Everything flowed from one thing to the next. Or no pesticides because I buy organic fruits and vegetables. Okay, in chemistry, none of those terms means organic. Okay. All of those are like just social definitions of the word organic. They don't mean organic in natural science. The word organic has a very specific definition. And what it means is it contains carbon. Yeah, it's that simple. So all your fruits and vegetables are organic, whether or not they contain pesticides, because they all contain carbon. Okay, so moving on to the next topic. Molecules come in lots of different sizes. Sometimes it's just one of something. That's called a monomer. Smallest form, just one of it. Sometimes we put two things together, like it's called a dimer, like a bicycle has two wheels. That would be a dimer. Sometimes we will put more than two things together. And we can have a chain of multiple things. That would be called a polymer. Poly just means multiple. And this polymer can be unbranched, like in this drawing, or it can have branches. Doesn't matter how it's arranged, it's still a polymer. And the last thing is a macromolecule. This means it has a very large number of atoms, usually in the thousands. Okay, so a polymer could only have four. That's not going to be a macromolecule. Okay, when we're talking of macromolecules, we're talking of four big categories of organic molecules. So, what are the four big categories of carbon containing molecules that have thousands of molecules in them? Well, in the title, I already gave you a hint that one of them was called carbohydrates. Okay, so knowing one's carbohydrates, what are the other three? Stop and think for a second. Okay, so most of you came up with proteins. Okay, some of you came up with fats. You're partially right. Did any of you come up with a fourth group? Probably not. Okay, so let's talk about how we're going to make these macromolecules before we start talking about. Yeah, I'm going to keep you thinking about it. Let your subconscious working on it for a little bit more. So how are we going to make these macromolecules? Well, the way we make the macromolecules is we have to take smaller molecules and put them together, right? Just like with little Lego pieces, you take smaller pieces and put them together. So we have to join two or more molecules. And the way this happens is we're going to lose water. So every time we have a monomer or a polymer, Notice that there's a hydrogen at one end and there's a hydroxyl at the other end. Notice there's a hydrogen at one end and there's a hydroxyl at the other end. And if there's a polymer, each monomer is bound, a little chemical bond, okay? And there's still a hydrogen and a hydroxyl at each end. And what is going to happen is the hydrogen from the end of one and the hydroxyl from the end of the other are going to be lost. And guess what they are going to form? Water. Okay. And then this bond is going to bind to that bond. And this is going to require energy to make a bond and to make a longer polymer. And because we are losing water, so remember in the summer when it's hot and you're losing water, we say we are dehydrated. But we are making something bigger, so that's synthesis. So this process of taking two shorter pieces and making something bigger is called dehydration synthesis, where two monomers become a polymer. And this is an example of an anabolic reaction where we are creating something. This is an anabolic reaction. Okay. So what if we want to do the opposite? What if we want to start with this long polymer and we want to end up with the short things? Well, do you understand we would have to break a bond for that to happen? And when we break that bond, we would have to end up with two smaller pieces, and we would need a hydrogen at the end of this one and a hydroxyl at the end of that one. So we would have to add water. In order to add water, we would have to split that water. Does that make sense? So that we would have a hydrogen go on one side and hydroxide go on the other side. So this reaction is called hydro for water, lysis, which means to split. So hydrolysis, or as we normally pronounce it, hydrolysis. So hydrolysis is going to split a polymer into two or more pieces. It's going to consume water. And because we are breaking a bond, we are actually releasing the potential energy that was stored in that bond. Because remember over here, we required energy, but remember, energy is never consumed or created. It's just changed from one form to another. So it's changed from kinetic energy to potential energy, and it's stored in that bond. And it's stored in that bond the whole time until we do hydrolysis, where now we are releasing it as kinetic energy. Okay, so that potential energy is being released. And this is an example of catabolism. This is a catabolic reaction. Okay, and in this example, it's showing we're going to have a polymer and a monomer, but we could have split the reaction here in the middle where we would have ended up with two dimers. Okay, so does everybody understand that? All right. So let's move on to those macromolecules. Did you figure out what the fourth one was yet? All right. It's time for some OChem. OChem stands for organic chemistry. There's four categories of organic molecules. Carbohydrates, I gave you. Lipids were the ones you were calling fats. Fats and oils together make up lipids. I will talk on a later video what the difference is between the two. Proteins was the third category. And the category you probably never thought of were nucleic acids. And yes, you do know what nucleic acids are. Let your subconscious work on that. Even if you don't think you've ever heard that word nucleic acids, you have heard that word nucleic acid many times in your life. We'll come back to it later. So let's get started on carbohydrates. And the first thing I want you to do is look at this word carbohydrate and break it down. What word do you know that looks like carbo? And what root did I just talk about that looks like hydrates? Carbon and hydrogen. Remember, I said hydro was water. So hydrogen and oxygen, water. So it wasn't hydrate as in hydrogen, it was hydro as in water. Hydrates is water. Just what I said a few slides ago, not hydrogen, okay? So carbohydrates are made out of carbon and water. So they're going to have carbon, hydrogen, and oxygen in that relationship. They're going to have one carbon for every two hydrogen and every one water. They're all going to be in that relationship. So one carbon to every two waters and one oxygen, only they're going to be split up to a positively charged hydrogen on one side and a negatively charged hydroxyl on the other side. So here's what glucose is going to look like. C6H12O6, okay? All carbohydrates are molecules made of the building block of sugars. For this course, consider that building block of sugars to be glucose molecules. They're not all going to be glucose molecules, but enough of them are going to be glucose molecules that you can just stick with glucose. And the thing about carbohydrates, sugar molecules are words that end in ose. Can you think of any other molecules that end in ose besides glucose? You should be able to. Okay, so we have simple carbohydrates. Examples of simple carbohydrates are going to be the monosaccharides, which have one sugar. Mono meaning one sugar, okay? Glucose, I just showed you. Glucose actually forms the six-sided ring, C6H12O6. Also, a C6H12O6 is fructose, which is the sugar found in a lot of our fruit. That's why it's called fructose. It actually forms a pentamer because it has a double bond carbon to an oxygen right here. Also, C6H12O6 is galactose. Now, some sugars are disaccharides, meaning they have two sugars. One that you do know about is sucrose, because sucrose is table sugar. It's actually not two glucose monomers, it's a glucose with a fructose. Okay. Lactose is the sugar found in dairy milk. It's a galactose with the glucose. You go, well, I never heard of galactose before, but you've actually heard of lactose, and one of the sugars in lactose was galactose. And then maltose, as found in like malt, as in like some beers, as well as malted milk balls. That's what is two glucose sugar. So you don't have to know what sucrose, lactose, and maltose are made out of. Just understand that they are disaccharides. They are two sugars, and yet monosaccharides and disaccharides are all examples of simple carbohydrates. And what does this mean? It means they are very easy for our bodies to break down, and they are simple for us to get quick sources of energy. There's no fiber in them. There's no vitamins in them. There's no minerals. They're just quick energy. They're going to give us a quick sugar boost. Now, in contrast, we can have complex carbohydrates, all of which are going to be polysaccharides, which are many sugars, as in hundreds or thousands. And there's different types of these. They vary how the sugars are aligned. Some of them are straight lines. Some of them have lots of branches. Some of them have nitrogen in them. Some of them will provide vitamins, minerals, and fiber. And these are the ones that we find in rices, legumes, Things like lentils, bulgur wheat, our other vegetables, our starchy vegetables, our pasta, barley, things like that would have complex carbohydrates. I want to talk about four different types of polysaccharides, which are very common in nature. The first is the category known as starches. I know you all know this word because we talk about starchy fruits and vegetables. A classic example would be potatoes. This is the chief form of energy that we store in plants. And when we look at this, what you can see is this is glucose, 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 glucose. It's a really, 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 really long unbranched chain of glucose molecules. And that's what starch is. So basically, we've just taken all these single monomers of starch and just made a huge, long, thousands of monomers long into a polymer. And that is known as a polysaccharide. The next type of polysaccharide is something known as cellulose, which you probably have also heard about. This is found in the cell walls as plants. This is the dietary fiber that we cannot digest, but other animals such as cows can. That's why they eat grasses and we don't. When we look at it, yes, it is glucose, 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 but notice that every other glucose faces the opposite direction. It has an alternating orientation, and that's what prevents us from being able to digest it. Okay, so how that happens is beyond the scope of this class. A third type of polysaccharide is something you may have heard about it, especially if you know anything about athletes and working out, and that is something called glycogen. And this is a storage form of energy that all of us have in our liver and our muscles, as well as other animals have it as well. And when you look at it, what you will notice, it is glucose all aligned, just like starch is, except that there is branching. And in the branching, the starch is all the equivalent of starch. The glucose monomers are all aligned in one direction. And they form these little spirals because they're all aligned. And this is glycogen. And when we see athletes, especially athletes doing endurance events like running marathons, they do that carb loading the night before where they're eating a lot of pasta and stuff. They want to make sure their glycogen stores are maximum because our bodies can store about 48 hours worth of glycogen for normal activity in between our liver and our muscles. But if you are running a marathon, you're going to run through those stores, especially if you're an elite athlete, long before you are finished with that marathon. So that's why they are consuming high energy compounds while they are racing. And the fourth type of polysaccharide, you may not have heard about it, but if you've ever encountered a creature known as a cockroach and stepped on it and heard that crunch, you have encountered the polysaccharide known as chitin because it forms the exoskeleton, the outside skeleton of arthropods, ticks, beetles, cockroaches, as well as some fungi. And that makes it the most common polysaccharide found in nature. It's very similar to cellulose in that you see it is alternating, but the glucose monomers, do you see how they're flipped? Every other one is flipped, but the big difference is that a hydroxyl group is replaced with a nitrogen group. So that is a biggie. So those are the four big types of polysaccharides. Okay, so that's pretty much all I wanted to cover in this section. So now I have a critical thinking question. I want you to bring in everything we've talked about chemistry so far to answer this question. So here it is. Think about it's the end of summer and the corn is at peak season. And you're driving, say you went out to Ojai and you were driving and there was corn and you bought some and you cooked it and you ate it. And it was the most awesome corn you ever had in your life. It was so super sweet. You thought, oh my God, this is so good. And so you went right back to the same stall and you bought some more corn. And you thought, oh my God, I'm going to have a date in a couple of days. And I want to share, like, this is nectar of the gods. And I want to share this with my loved one. So you went home. Okay, you're poor. This is what your refrigerator looks like because, like, we can't afford for those cutesy little refrigerators. So you put your corn in your refrigerator and you let it sit there until the weekend. And now you have this dinner date and you cook up the corn and you expect your date to have these throes of ecstasy eating this. Oh my God, this corn was so awesome. Oh my gosh. And this is the reaction that you get from your date. And your date goes, sweet? This corn wasn't sweet. That's not the term I would use to describe this corn. There's a few other choice terms I would use. So I want you to stop and think, what happened chemically to this corn? And please don't take the easy way out and tell me the corn went bad, because that's not the answer. Don't tell me my refrigerator quit working, because that's not the answer. Don't tell me my date's taste buds must not be working, because that's not the answer. Tell me about the chemistry involved. Okay. And feel free to write me through the Canvas inbox and let me know what you came up with. And I'll tell you if you are right, or I'll tell you if you're on the right track. Okay. Because I know everybody should be able to figure this out. All right. And with that, we're done with this section. I'll soon see you soon for the next one. Thank you so much for working hard.